Hello, everyone. This is the West Region Sales Manager for MAR Opto, a division of MAR, the optics division of MAR. And we'd like to thank you very much for joining the challenges and opportunities for A-Sphere and freeform metrology today. Very much appreciated. Prior to us getting started, I'd like to cover a few things about questions and raising hands. We definitely welcome all questions, from the simplest questions to the most complex questions. If we can't answer them today, we'll definitely get back with you to provide an answer. But nevertheless, you can raise your hand at any point during the webinar. In some cases, we may not be able to get to your question right away. We do have a time allotted towards the end of the webinar, around 10 to 15 minutes specifically for questions. So we'll be reading off questions, and then for those questions that we don't get to, and we do apologize for that, we may not, if there are a lot of questions, we will email that individual person that had the question with an answer. So you should be able to, under the attendees, or in your in your dialog box to the right of the screen, you should have a way to raise your hand, and then you should also have a section for questions where you can send a question directly to us. You can send that privately, or you can send it with everybody included. So please ask away. Without further ado, I'd like to get started. And again, my name is Byron Siebel for those that are just joining. And we have Dr. Brent Bergner, our optical scientist out of Tucson, Arizona, joining us. So, Brent, do you mind to change the slide?
Sure.
So just a little bit about MAR. So MAR has been around for about 157 years, or 150 plus 7 years. So started in Esling, Germany in 1861. We were a global company. We're in about 60 countries, about 18 subsidiaries within those 60 countries, and MAR Incorporated being one of them, based in Providence, Rhode Island, which I'll discuss in just a second. But MAR is involved in every possible application dealing with precision gauging, dimensional metrology, or metrology systems, and now more specifically in our industry, optics. So that's just a little bit about MAR. About 2,000 plus employees, so we're a very, very large company, a very large network of support and service. Please, Brent. These are just some big name customers that we've worked with over the years in the United States and in Europe and Asia and all over the world, just to give the audience a breadth of sort of who we work with and how we work and some of the industries that we're working in. Brent?
Okay.
More specifically, this slide gives you a brief overview of MAR's history. I won't cover everything in detail. I just wanted to give the audience just a quick overview. Specifically for MAR Opto, about 2004, MAR created a division, which I've mentioned a couple times so far, as MAR Opto, based out of Jena, Germany. We're actually located in the Zeiss facility on the 7th floor, and that's where the majority of our R&D takes place. In about 2015, which was about 2.5, 3 years ago, we acquired a company out of Tucson, Arizona, or MAR acquired a company out of Tucson, Arizona called ESDI, which joined the MAR group, which is now MAR. MAR took all their profilometry experience and all their precision gauging experience from the dimensional and PG side of the world, and then incorporated the Fizeau and interferometry metrology systems into the product portfolio to give a full I guess, a symmetry to their product offerings for the optics community. Brent? More specifically, we have three centers of excellence, which one is in Shanghai, China, one's in Jena, Germany, and the other is in Tucson, Arizona. But more specifically, for optics, our headquarters is in Providence, Rhode Island for the Americas. We have our service support center out of Erlanger, Kentucky. We have Charlotte, North Carolina. We have a location in Cyprus with the full demo facility. And then Tucson is where we manufacture the Fizeau interferometers. And also we have our engineering support and application support out of Tucson as well for the Americas. And just a quick, I won't go through this, all this information, but nevertheless, we have, as I mentioned before, we have a wide breadth of products ranging from the very minute precision gauging systems, which have our latest integrated wireless technology for the shop floor, all the way to the basic Fizeau interferometers for 40 millimeter apertures, all the way to beam expansion up to 300 millimeter, profilometry, contact, non-contact, and A-sphere metrology, specifically non-contact A-sphere metrology systems as well. And so that's basically it. I just wanted to give a brief summary of who MAR is, what MAR does, and what MAR offers. And without further ado, I'd like to hand it over to Dr. Brent Bergner, our optical scientist out of Tucson, Arizona, to start talking about the challenges and opportunities for A-sphere and freeform metrology. Thanks again.
Well, hello, everyone, and thank you, Byron. Again, I'm Brent Bergner. I'm the senior optical engineer here in Tucson, and I'll be giving the presentation today. But first, I would like to thank our colleagues in Jena. Most of this data was taken by them on tools there in Jena, and a lot of the slides that I have, I either modified or just completely ripped off from them. So I would like to thank them, that group there. And the first thing I'd like to do as we get into talking about the metrology for freeform and A-spheres metrology is talk about what I mean when I talk about an aspheric surface and what I mean when I talk about a freeform surface. So for the aspheric surfaces, I really mean any a rotationally symmetric surface that has a cross section that deviates from a sphere or a flat. These might also be sections, off-axis sections of such surfaces, such as an off-axis paraboloid. The nice thing about aspheric surfaces is that they do have some sort of a natural reference, which is where the axis of symmetry crosses the surface. But because they are not spherical surfaces, because they have extra mathematical terms that describe their deviation from a spherical surface, they have extra degrees of freedom that the optical designer can use to either reduce the number of elements, improve the performance of a system, reduce the size of a system. So they're very desirable in terms of being able to design a system. However, I remember when I was first learning about optical design back in the early 90s, my professor said, "Don't worry about aspheric surfaces. You'll never see them. They're too hard to make." Well, my entire career since then, I've been working with aspheric surfaces. So they're becoming easier and easier to make, or more reliable to make, and they're being incorporated into more and more systems. And so that's why it's important that we figure out how to measure them in a good way. Aspheric surfaces, as I said, deviate from a sphere, and that deviation is often described as a section of a conic plus some sort of polynomial terms. The standard way of describing that is just a set of polynomial terms in powers of the radius. But then a few years ago, Greg Forbes came up with a method of orthogonalizing those terms, and he calls those the Q polynomials. And I think in common parlance, people have started calling those the Forbes polynomials. But however you describe the surface, it's important, since there are so many ways to describe the surface, however you describe the surface on your optical drawings, it's important to also include a table of the sags, the deviation from a flat of the surface, a table of those sags, so that when the person puts the equation into their generating machine, or we're trying to compare it to some measured data, we're able to compare the as designed to the as measured or as generated surfaces. And we make sure that we're all using the same equations and the same coefficients. So for freeform surfaces, they have no particular axis of symmetry. And so there's no particular reference for the surface. And so it's always important to be able to, in the design, define some surface, define fiducials, and define datums that can be used to reference the surface to the generating machine, to the measurement machine, and to the final application. Freeform surfaces aren't necessarily new. Here's an example from the literature of a Polaroid camera that used freeform surfaces back in the early 70s. But they are very flexible because they have so many degrees of freedom. You can do just about anything with them. And there's an example up here on the upper right of being able to take a Gaussian a Gaussian field and intensity field, and then use a freeform optic to actually form a picture by focusing the light in different points on the image plane. But most of the time they're used, just like freeform optics, to reduce the number of surfaces, to improve the optical performance, to reduce the size of systems. And here's a demonstrator on the lower right-hand corner. Here's a demonstrator project that was funded in Germany through the Fraunhofer Institute, where they were able to design and fabricate a monolithic night vision objective. And this has several freeform and aspheric surfaces all into one piece of glass. And I'll talk a little bit about the description of that later. Oops. So however, whether it's a freeform or an aspheric surface, you need to be able to make it. Flats and spherical surfaces are relatively easy to make because they can be made through random processes. But freeform and aspheric surfaces need to be made through some deterministic generating process, such as diamond turning or deterministic grinding and polishing, like is used in the QED magnetoradiological finishing system. Aspheric surfaces can be turned on a high precision lathe, such as a diamond turning machine. And then you can also use those high precision lathes to do, let's see if I can get this video to work here. You can also use those high precision machines to make freeform surfaces by moving the tool back and forth in synchronization with the rotation of the spindle. Oops. Well, you're going to see that again. But however you're making the surface, you have to be able to measure it in some way to give feedback to the generating process, whether it be a tool path correction map for a diamond turning machine, or a dwell map for a grinding and polishing machine, or parameter sets for molding systems. And that's what I'm going to talk about for the rest of this talk, is how do you take those measurements to give that feedback to the generating process. And so I'm going to go through several different sets of kinds of techniques, including scanning profilometry, different sorts of interferometric methods for measuring aspheric surfaces, and then briefly talk about geometric slope tests such as the Hartman test, and finally finish up with some of the future of where I think that aspheric and freeform metrology is going in the near future. And the format of this talk, I will give a brief description of the technique, and then I'll bring up this table and we'll fill in this table as we go along with the different advantages and disadvantages for each technique. I'd like to acknowledge that there have been several other groups that have done similar tables, and after I first built this table, I realized, I'd seen this somewhere else, and it was in a very, very good application note that Optimax put out concerning aspheric metrology. So the first technique I'd like to talk about is simple 2D profilometry. This is where you're dragging a stylus across the surface and looking at the deviation of the stylus with respect to position. And you get a 1D trace of the surface, and for final applications, you would rather have a 2D trace of the surface, but in some applications, such as when you're first starting to grind the surface, a 2D trace is perfectly fine. I know that a lot of the optics people out there get cringe a little bit when you talk about dragging a stylus across the surface, but we are able to adjust the force of that stylus on the surface electronically in one of our systems, the MarSurf LD260, and we're able to reduce it down to forces of down to 0.5 millinewtons. And so we've been able to measure some very soft surfaces with this and prove that we weren't scratching the surface by taking a scanning white light interferometer of the surface before and after the scan. But of course, always test the surface before you do anything like this. But it gives you some very straightforward data. You can fit the curve and you can understand what the surface looks like. Now, if you do want a 2D map of the surface, you can either probe the surface using a conventional CMM. Zeiss actually has some CMMs that are specifically made for measuring freeform surfaces, freeform optical surfaces, in fact. Or you can, MAR is very good at measuring cylindrical surfaces. And so we have several systems that have a precision rotary bearing where we spin the part underneath the probe. And so by setting the probe at some distance away from the vertex of the surface and spinning the part around, we can get a trace of the height of the surface along a circular path. And if we set the probe at different distances from the vertex, then we get a set of concentric profiles of the surface. And then we can fit a surface to those concentric profiles and get an idea of what the 3D surface of the lens looks like. So we're also able to use optical probes for doing this. We've got another system called the MFU200 that uses an optical probe where we're able to measure the distance between the surface and the tip of an optical fiber. We illuminate the surface through the optical fiber with a broadband light source, and then because there's some distance between the tip of the fiber and the surface, wherever that distance is 1/2 of the wavelength of any particular wavelength coming out of the fiber, you get destructive interference, and then we're able to record the constructive and destructive interference of the light with respect to wavelength in a correlelogram. And the peak of that correlelogram tells us the distance between the tip of the fiber and the surface under test. So now we operate the system in two ways. In one way, we monitor the wavelength of the peak of the correlelogram as we scan the part under the tip of the fiber. And that's the way that we usually measure an aspheric surface. Or we can try to move the tip of the fiber up and down to keep the peak wavelength, the wavelength of the peak of the correlelogram constant. And then we record how far we had to move the fiber in order to keep that peak at the same wavelength. And so that's an active tracking method that we can use to measure any sort of arbitrary form, like a freeform surface. So here's an example of how we use the MFU and the interferometric probe to measure a freeform surface. So we measured the surface and got a surface map of the height of the surface with respect to position. And on this surface map, there's two surfaces. There's a freeform portion and there's an aspheric portion of the surface. We masked out the aspheric portion of the surface and then subtracted that from the design surface to get a deviation map of the surface with respect to design. And then Sphericon was able to use that as a dwell map to correct the errors of that surface. And that was used in this, this demonstrator monolithic night vision objective that was developed by Fraunhofer. Whenever you're measuring a freeform surface, as I alluded to before, there's no natural way of referencing that surface. And so you need to be able to reference alignment features on that surface to your generating machine, to your metrology instrument, and to the final system. And so here you see in this case, we've created a kinematic mount that the optic lays on top of. There's three balls underneath the optic that define the plane of the optic, and then we've got two balls here and here, which reference the features that were machined into the blank of the optic. And now when we're generating the optic, when they're manufacturing the optic, they can take that optic, put it on the metrology tool, take a measurement of that surface, then take it back to the generating machine and use those same features on the substrate of the surface to align the optic to the generating machine. And then finally, once they have the surface that they want, they can use those same features on the blank of the surface to align the optic into the final system. And one further consideration to think about when using aspheric surfaces in particular is the alignment of the axes of the surface. Whenever you have two spherical surfaces, there's always some line that you can fit between the centers of those two spherical surfaces, which define the axis of that particular element. And then often you'll use that line to reference it in the edging machine, and you can define the mechanical features of the lens to line up with the optical axis of both of those surfaces. However, for an aspheric surface, since there's an axis of rotation that's specific for each surface, there's no way to, if you've got two aspheric surfaces and an optical element, there's no way to align both of those surfaces, both of those axes together. No natural way of just putting a line through both of those axes. So you need to be able to measure the tilt between the axes of both surfaces. And then you also need to be able to reference that to the mechanical edge of the element. So one of the ways that we do that with the MARSURF, the MFU 200, is we're able to measure the optical surface, one of the optical surfaces, using the non-contact interferometric point sensor, as I talked about earlier. And then we have another, if you can see that off to the right of that interferometric point sensor, there's another mechanical probe on that same arm. And so we just rotate the arm around, and we're able to use that to pick up the edge of the element that we're testing. Without moving the element, we just rotate the arm around and we pick up the edge. And then we use a third probe on that arm to pick up the underside of the element. And so now on one machine, without moving the element under test, you're able to pick up the front surface, the back surface, and the mechanical edge of the part, and register all three of those together and get information about the tilt and decenter of each of those surfaces. So some of the advantages of scanning profilometry is that there's no real symmetry required for the part. You can measure just about anything, well, within reason. It can measure large departures of the surface from a reference surface. However, you're limited in the precision of a mechanical profiler to about 50 nanometers or so. And some, depending on the profiler, some are up to 5 micron precisions. But the MFU, for example, can go down to about 50 nanometers. And there's a large variety of price points for these instruments, all the way from a few tens of thousands of dollars to some of the precision CMMs that could cost up to $1 million. And one of the things that I didn't mention about these is since you're not since for the mechanical probes you're not really relying on any sort of reflection from the surface, you can measure ground surfaces with these. So you can measure the surface early in the process. The rest of the talk is going to be about mostly about interferometric methods, and so I don't think for this group I really have to go through this too much, looking at the names here. But for anyone out there that's listening that is not familiar with interferometry, interferometry is looking at the distance between two surfaces, or the interferometry that I'm going to be talking about is looking at the distance between two surfaces using the phase of the light reflected from both of those surfaces. And so if I have light reflected from this top surface, this is my test piece here, and then I reflect light off of this bottom surface, my test piece here. If that light is in phase, then what I see up here is a bright line, or a bright spot, because that light interfered constructively. Now, if they're an odd number of half wavelengths out, I see a dark spot because they interfere destructively. And if I keep going across the surface, the distance between two of the same point on that, we're going to call that a fringe. The distance between two similar points on that fringe is going to be a fringe spacing. And so I will get fringes across until I hit some sort of a deviation in that surface that's going to show up as a bend in that fringe, and the bend in that fringe then is going to be related to the height of that deviation of the surface. And so you can kind of think of this fringe pattern as a contour map of the surface, and as the difference between these two surfaces becomes steeper and steeper, this fringe pattern is going to become closer and closer together until you can't resolve it with your imaging system. And so that's one of the problems that I'm going to talk about in each of these systems. So some of the unique considerations when you're measuring an aspheric surface as opposed to a flat or a spherical surface using interferometry is that often these generating techniques that I talked about, they are going to cause, excuse me for a second. There we go. They're going to cause mid-spatial frequency errors, so errors that are not quite form errors, they're not quite roughness errors, but they're these often periodic errors in the surface that are in the order of 10 line pair to 100 line pair per millimeter, that are very difficult to resolve with conventional interferometry. But they are very important for controlling the process. With interferometric techniques of measuring aspheric surfaces, you'll also often have surfaces that have some inflection point in them. And interferometry has a hard time of measuring that inflection point because the rays cross each other and you can't really tell what portion of the surface the rays are coming from. the results of measuring a aspheric surface with interferometry are often very sensitive to alignment, and that alignment is often very difficult. So it's hard to separate errors in the surface from errors in the alignment of the parts of the interferometer. And then for a certain set of tests that I'm going to call a non-null configuration, where the shape of your reference surface is quite different from the shape of the surface under test, there's going to be additional problems. At least part of the surface is always going to be out of focus, and so you're not going to be able to resolve those high spatial frequency features that you're looking for in the aspheric optic. There's going to be large slope errors, which are going to make those fringes become very close together, and you're not going to be able to resolve those. There's going to be a large range of spatial frequencies that you're going to be interested in, which means that you can't put apertures in the interferometer to filter out stray light, and so stray light can become a problem. But there's basically a trade-off, though, between what kind of spatial frequencies you're able to measure, how high a slopes you're able to measure, and controlling the stray light. And then finally, because the rays don't go back through the interferometer in the same way, the interferometer is going to induce errors in the measurement. They're going to be dependent upon the surface that you're testing. And we're going to call those retrace errors. And so it's important to do very careful calibrations of the interferometer to be able to characterize what those ray trace errors are going to be for any particular surface. So the first technique that I'd like to talk about in testing aspheric surfaces is one that's often used for testing sections of conics. So a conic surface always has a stigmatic point or a set of stigmatic points. And you can use those as a way of testing the A-sphere with a spherical reference. So, for example, in this case, for testing a parabola, the interferometer is going to create a spherical reference wavefront using a transmission sphere that's going to focus to a point. And if you put that focus point at the foci of the at the focus of the parabola, then the parabola is going, if it's a perfect parabola, then it's going to perfectly collimate the light, and you're going to get a plane wavefront that then hits this reference flat. So this reference flat then retroreflects that collimated light back to the interferometer, back to the parabola, and if the parabola is perfect, it's going to perfectly focus the light back to the focus, and then that's going to create a wavefront that's going to interfere with the test wavefront. And if you're all lined up and everything is perfect and the shape of the surface is perfect, then you get a null fringe. And any deviation from that is either due to misalignment of the system or due to an error in your surface. And so you're able to do this for many conic sections. For example, here's an ellipsoidal surface, and it's often used in testing these surfaces, these surfaces off axis. It's a very useful technique. You can measure the surfaces with interferometric precision of tens to hundreds of nanometers. You can only measure conic surfaces or surfaces that have stigmatic points, where you can get access to those stigmatic points. So that really limits the usefulness of the technique. You cannot measure large departures of the surface from its design. And it really doesn't take long to take the measurement, but it can take hours to set out the measurement because it's so hard to get the alignment right. And it's a fairly cheap test because all you need is the conventional interferometer that you might already have in your optics shop, plus some auxiliary optics, and of course fixturing to be able to align everything. And fixturing can be very important in this setup. If you fixture things right, it can make the alignment a lot easier. The next technique that I'd like to talk about is kind of extending that to create an arbitrary an arbitrary reference surface. And you can create these arbitrary reference surfaces by just designing an optical system that creates a wavefront with the desired shape using refractive null lenses, such as the Offner lens that I have shown here for testing parabolic surfaces. Or you can generate that reference wavefront by using a computer-generated holographic surface, or even a conventionally generated holographic surface. But for the computer-generated holographic surface, you can basically design an arbitrary diffractive structure to generate an arbitrary wavefront to compare with the surface under test. And you can make these fairly well and very precisely using E-beam lithography and etching techniques that were developed for the lithography industry. And one of the nice things about using a computer-generated holographic null is that in addition to making the pattern to generate the wavefront that you're interested in, you can also precisely put other patterns on the same substrate at the same time that you can use to align the CGH to the interferometer and align the test optic to the CGH. So you can really improve the ability to align the CGH to align the system. So for refractive nulls and computer-generated holographic nulls, you can still measure with interferometric precision. You really can't measure any surfaces that deviate a lot from the wavefront that you generated with the null system. But they can be very fast to take the measurements, but it can take weeks to months to actually make the systems to generate the null surfaces that you want. And those can be fairly expensive. For example, for a computer-generated holographic null, anywhere from $5,000 to $20,000. So if you're measuring a particular one surface over and over and over again, and you can amortize that cost and the setup time over all of those lenses, this can be a very, very good solution to measuring your aspheric or even freeform surfaces. Another method of measuring highly surfaces that depart a lot from the reference surface is to just use a longer wavelength. And so here's an example of an interferometer made with a CO2 laser at 10.6 microns. So this has about a sensitivity of about, what was it, 7 times less than your conventional 632 interferometer. And so you're able to measure not only surfaces that deviate a lot from the reference surface, but you're also able to measure rough surfaces because at those longer wavelengths, the rougher surface still looks specular. Another way of achieving measuring a surface that deviates a lot from the reference is to just measure the surface using 2 different wavelengths. And you will get interferograms back from each of those wavelengths that you may not necessarily be able to resolve with the detector that you have. However, those 2 interferometric patterns are going to combine together in a moire pattern that does have a fringe density that is a fringe density that's large enough so that you can measure it with a camera. And basically, you're measuring then you can think of it as measuring with an interferometer with an equivalent wavelength that's the geometric mean of the two measurements that you're measuring it with. And so IR interferometry and two-wavelength interferometry, you can measure very large departures from the reference surface. However, you're limited to measuring in your precision to the wavelength or the equivalent wavelength that you're measuring with. And you can get very fast measurement times. The setups are fairly straightforward. And the instruments can be slightly more expensive than conventional interferometer. Another way of getting around the high fringe densities is to use sub-Nyquist interferometry. In conventional phase shifting interferometry, you're depending on a difference in intensity on a pixel as you vary the distance between the reference and the test surface. So as you vary the distance between the reference and the test surface, the fringes shift, and you're worried, you're depending on the intensity on a particular pixel in your detector array as you're shifting these fringes to get information about the surface. So if you have fringes, more than one fringe that covers a pixel, when you do that shift, then your measured intensity doesn't vary on those pixels where the fringe density is too large. However, if you put a pinhole mask over that detector array, so you're only looking at a very small area, you're only getting light from a very small area that pixel over which that pixel covers. And now you do that fringe phase shifting. Watch this one pinhole here and that one fringe. Now when you do that phase shifting, you do get information about the wavefront at that particular point. And then you can use conventional phase unwrapping algorithms to fit the surface to that data. But that might give you an incorrect answer if the fringe density is very large. And so you add an additional constraint to the phase unwrapping algorithm so that you're not only matching making sure that giving the constraint that the surface is continuous, you're giving a constraint that the derivative of the surface is continuous. Then you can get if those two things are true, you can get a more good representation of what the surface looks like by using the additional constraints in the phase unwrapping algorithm. One final thing that we do with the sub-Nyquist interferometer is, even though you're getting the phase shifted data of the interferogram, when you look at the fringe pattern on the detector, you get this big mess because the fringe density is too high and it's aliasing, and you get a lot of you don't get anything that you can use to align the optic to the interferometer. However, if now I take an ideal version of what that interferogram should look like that I calculate inside the computer, and I add that pixel by pixel to the measured interferogram, I get a moire pattern. And I can use that moire pattern to align the optic under test to the interferometer. And so sub-Nyquist interferometry now, I can measure very large, now I can measure large departures of the surface from the reference. I can measure it with interferometric precision. I can basically do a large range of surfaces. The setup time and the measurement time is comparable to conventional interferometers. And of course, because you have to put this mask on top of the detector array and do all these extra things in the interferometer, these instruments are slightly more expensive than a conventional interferometer. And we are now redeveloping this interferometer here at MAR. And another technique for measuring large departures from the reference sphere is just to use different reference spheres. or measure the part at different points. So you're fitting different radius or curvature spheres to the surface. And here's an example of how Zygo does it with their Verifier A-sphere tool. They take the part and they move it along the optical axis, and each time they move it along the optical axis, they're actually able to resolve fringes in a different portion of the aperture, of the pupil, I'm sorry. And so by moving the part and getting fringes that they can then fit a surface that they can analyze and fit a surface to in each of these annular zones, they stitch together those annular zones to get a map of a complete surface. QED has another technique they use for stitching together areas of the part to get a complete map of the surface, and they're basically moving the part so that they get resolvable fringes over different areas of the part for different orientations of the part, and then they make these areas overlap so that once they've determined the form of the surface over each of these small areas that overlap, they can stitch those together to get an idea of what the entire surface looks like. Another interesting thing that they do with that is they use a variable optical null. So they put two flat wedged pieces of glass between the reference surface and the part under test, and they rotate the orientation of that wedge with respect to each other to create different aberrated reference wavefronts that fit the surface better than the pure spherical wavefront. And so with that, they're able to cover larger areas of the surface under test and use less sub-apertures that they need to stitch together. And so now stitching interferometry is able to measure large departures from the reference surface. It's able to do it with interferometric precision. The setup time isn't very long. However, the measurement time can be fairly long because you have to take multiple interferograms and mechanically move the part or move the interferometer between each of those measurements. And these instruments tend to be expensive, around the area of $500,000 or so. So a method that MAR is developing that was originally proposed and initially developed by Wolfgang Osten's group in Stuttgart is called the tilted wave interferometer. So for a standard interferometer, you have a point source that then is collimated and focused using the reference optic to create the reference wavefront for the part under test. And now if I take that point source and I move it, so I get an interferogram just like in the stitching interferometers. Now if I take that point source and I move it, then I'm actually tilting the reference wavefront with respect to the part under test. And if I move that point source to another spot in the entrance pupil, I get another wavefront that's tilted with a different angle with respect to the part under test. And I continue to do that. And so now I get a series of interferograms, each with a different tilted wavefront. So that would take quite a while also. But what Osten's group realized is that instead of moving the point source, you can create a bunch of point sources using a lenslet array. And so that's exactly what they did. Is they created hundreds of point sources by putting a lenslet array in the pupil. And so then they can phase shift the interferogram, and they get a set of phase shifted interferograms that are a combination of the interferograms created by each of those point sources. One of the issues with this is that the interferograms from adjacent point sources will overlap, and you won't be able to distinguish the phase shift, the information from one of those lenslets from the lenslet next to it. And so we put a multi-lens aperture into the system that blocks every fourth lens, or blocks 3 out of every 4 lenses. So we're only looking at the information from every 4th lens. And then we move that aperture around. So now instead of moving the part and needing to move the part very precisely, all we're doing is moving an aperture around to get information from a whole set, a bunch of parallel information at once. So we get 4 sets of information from each position of that multi-lens aperture, and that positioning of the lens aperture doesn't have to be as precise as the positioning of the surface for stitching. And so we get 5 sets of interferograms that we're then able to determine the phase and unwrap the phase and determine the surface shape for each of those 4 sets of interferograms, and then combine those to get a map of the entire surface. And here's an example of doing this for a fairly mild A-sphere. This one has a gradient, a deviation from spherical of only about 4 degrees. But with this technique, we're able to do deviations of up to about 8 to 10 degrees, which is significant. And then we're also able to measure freeform surfaces. And here's an example of a freeform artifact that was made by PTB, the German equivalent to NIST. And it consists of 2 spheres that are laid out on the surface. One sphere with a radius of 39.5 millimeters and the other one with a radius of 40 millimeters. And they kind of create this undulating surface that we were then able to measure using this tilted wave interferometer technique and compare that to a trace of that same surface using the interferometric point source scanning technique that I talked about earlier. And we saw that those correlate very well together. And so then the tilted wave technique now, you can measure large departures again, just like for the stitching interferometry. You can measure them with interferometric precision, just like for the stitching interferometry. But now instead of taking tens of minutes to take an individual measurement, because you have to move either the part or the interferometer, now you can do it in minutes because all you're moving is that subaperture array so that you're not getting conflicting data between the different point sources. And it's equivalent in price to the stitching interferometers. So we are now in pre-production with this. We have several instruments in the field with select customers, and we're gathering data and gathering user experience from the instruments so that we can introduce those sometime next year. I'd like to throw in also geometric tests, such as the Hartman test or the knife edge test. These tests in general are more qualitative than quantitative, although there are quantitative versions of each of these tests. And I'll actually talk about, in a slide or so, talk about another method called deflectometry, which is a quantitative version of a reverse Hartman test, they like to refer to it as. But each of these tests, you've got the wavefront, and you're deviating the wavefront some way using the test and observing that deviation of the wavefront on a detector. And if everything were perfect, then for example, for the Hartman test, if everything were perfect with this wavefront, then all of these points, all these lenslets would focus right at the center of each of the reference points on the focal plane, and and any deviation from perfect causes the point to shift in the focal plane. So geometric tests are very nice in that they can measure large departures. They can't really do the precision of interferometric tests, but they can be really cheap to set up. And so it's a good secondary test to make sure that all of the expensive tests that you've made you haven't done some alignment incorrectly. So I'm a big fan of being able to use geometric tests to check on the interferometric tests that you're doing. And one of these geometric tests that I think is going to be used more and more in the future is what is now termed deflectometry. And the group over at the Mirror Lab at the U of A is using deflectometry to a lot of advantage. And basically what they've got is they just hang a big screen TV above the optic with a series of lines on it. And those lines are reflected by the optic, and they look at them with a camera. And when the lines from the camera are reflected by a curved optic, the line itself will curve. And they're able to phase shift, they're able to move these lines back and forth, look at how the lines on the image, in the image plane change, and then calculate the shape of the surface from that. One of the important parts of this, though, is you need to be able to calibrate it very well. You need to know the exact distance from every point in the display to every point on the surface under test, to every pixel in the camera array. You have to know all those distances very precisely, and so there's a lot of calibration techniques that they worked up for determining those distances. So that's a very neat technique. And another technique that I think will be used more and more for measuring the shape of surfaces, which has been used in the past for measuring measuring the shape of wavefronts to great advantage, is phase retrieval. And with phase retrieval, you're moving an aperture around the pupil, and you're recording the intensity on a CD on a camera, a detector array, for every position of that aperture, every position of that sub aperture. And using ray tracing, you can, if you know the shape of the wavefront that's hitting the surface under test, and you know what the surface under test looks like, and you know very precisely where that sub-aperture was and what the shape of the sub-aperture is, you can calculate what the intensity pattern on the detector is going to be. So now, if you've got a model of the measurement and you've got a measurement, then you can compare those two together and see if they match. Well, if they don't match, then I tweak something in my model, such as maybe I change the shape of one of the surfaces on the lens in my model, and I recalculate the model. And then I see if it matches again. And I keep going around and round in this cycle until I get a measured result that matches the modeled result. And when I've got a measured result that matches the model result, I say, ha, now I've determined to some degree, now I've determined what the shape of that surface looks like. And I think I call this model-based measurements, and I think the model-based measurements are going to be more and more important for being able to determine the shape of surfaces with low uncertainties for just about any of these techniques. For example, this deflectometry technique, a model-based measurement, could be used to determine the relationship of the different by using the positions of the camera, the display, and the optic. They can be used to determine those positions in the model-based measurement. And so with that, I'd like to finally let you guys go. This is a summary of what I've talked about. And you can see from the summary that there is no perfect technique for doing every measurement that you need to make on aspheric and freeform surfaces. But hopefully I've given you some idea of the advantages and disadvantages of each technique, so then you could use that to pick the measurement, the metrology techniques that are best for your particular application. With that, I think we're ready for any questions and answers. Well, hopefully.
Thank you so much, Brent. Yeah. Yeah, so thanks again to everybody that stayed with us through the webinar. We much appreciate it. So we'll open the floor, like Brent said, to any questions. Just raise your hand, or just type in a question and send it to us. But in the meantime, again, thank you for joining. I think the majority of the people that joined us today, Brent, and I think we sent out a large number of invites, but we'll continue to keep sending out invites for this webinar series. We'll be doing a joint webinar in third quarter. The date is yet to be determined, and we're partnering with a local company in Southern California to talk about freeforms specifically, not only the manufacturing, but the challenges of fixturing freeforms for measurement. So that might be an exciting topic for some of you that had joined today. So look out for that. And then we're already diligently working on our fourth quarter webinar, which the topic is yet to be decided, but I think it will be just as interesting as you have seen in the last two webinars that we've hosted. So please do keep joining, and hopefully some of the information is useful for you guys to make determinations for your manufacturing, for your thesis, or whatever the application might be. So I don't see any questions as of now. Just a heads up for everybody, we will be posting this on our MAR Exactly YouTube. So please go to MAR Exactly on YouTube and subscribe. And all of our webinars will be posted there for the free to watch. You can download the webinar and the presentation off our MAR Exactly site. You will receive an email after all this is said and done, probably beginning of next week, where you can download all that information for your private viewing or for your colleagues that were not able to join today. So without further ado, I think we'll probably wrap it up. If you have any questions, you will receive an email from me directly as well, just saying thank you again. And if you have any questions, you can reply to me on that email, and then we'll take consideration and send you an answer from there. So without any hesitation, I think I'm going to close it out. So again, everybody, thank you for your time, and I hope you have a wonderful rest of the week.
Thank you very much.